Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Now, after an introduction about the membrane, we start the selection of the membrane process. For selection process, these steps have to be done. You have to have a knowledge of the membrane size, particles or molecular size, and etc. You need to know about the membrane materials, properties, advantage and disadvantage of these materials, and also types of the modules and operating mode. Let's start with the first step. Determination of the necessary molecular separation size of the membrane to be chosen. Classification of membrane and filtration processes. The membrane processes, microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, are classified according to the size or molar mass of the separated substances. Their different molecular separation size allow for the choice of the suited process for the particular task. In this figure, you can see a classification of membrane based on the size in micrometer, molecular mass, and the substances that can be separated by these membranes. There is a size range from 1 to 0.001 micrometer with an approximate molecular mass from 500,000 to 100 Dalton. We will discuss each of which in detail. Microfiltration. Microfiltration is an important and widely used separation process among other membrane processes. Microfiltration comes under the category of low-pressure membrane processes due to the use of an applied pressure below 2 bar. Microfiltration refers to filtration processes that use porous membrane to separate suspended particles with diameter between 0.1 to 10 micrometers. As you can see in this animation, microfiltration membranes are capable of separating large suspended solids such as colloids, particles, fat, and bacteria while allowing sugars, proteins, salts, and low molecular weight organic compounds pass through the membrane. There are two principal types of microfiltration membrane filter: depth filters and screen filters, and you can see in this figure the apparent differences of them. While screen filters have small pores in their top surface that collect particles larger than pore diameter on the surface of the membrane, depth filters have relatively large pores on the top surface so particles pass to the interior of the membrane. The particles are then captured at constrictions in the membrane pores or by adsorption onto the pore walls. Screen filter membranes rapidly become plagued by the accumulation of retained particles at the top surface. Depth filters have a much larger surface area available for the collection of the particles, providing a larger holding capacity before fouling. Screen membrane filters are preferred for the cross-flow microfiltration systems, but depth filters are usually preferred for dead-end operating mode. For better understanding of the microfiltration in removal of the substances, an example has presented. A list of substances has presented including non-dissolved substances such as bacteria, parasites, inorganic particles, and viruses, and dissolved substances such as high and low molecular weight organic compounds, intermediate organic compounds, multivalent and monovalent ions. Now specify the substances that can be removed using microfiltration. As you can see, the answer is only bacteria, parasites, and inorganic particles that can be removed using microfiltration due to the larger size than this filter. It has to be also noticed that virus cannot be removed using microfiltration. Microfiltration applications. Microfiltration is a physical separation process which removes contaminants such as suspended solids, fats, and microbes from process fluids. Microfiltration may also be used in combination with other membrane technologies such as reverse osmosis, nanofiltration, and ultrafiltration. Common applications of microfiltration membrane technology include water and wastewater treatment, dairy, food and beverage industries, and etc. For example, in industrial process wastewater treatment such as oil refineries, petrochemicals, power plant, or sterilization of beverages and pharmaceutical to remove bacteria and other undesired suspension from liquids. In water treatment, removal of turbidity from surface water for potable supply, or a key step in the primary disinfection including removal of pathogens such as the protozoa cryptosporidium, which are responsible for numerous disease outbreaks. Microfiltration usually serves as a pre-treatment for other separation processes such as ultrafiltration, reverse osmosis, and a post-treatment for granular media filtration. In wastewater treatment, also clarification of biologically treated effluent in membrane bioreactors. In dairy industry, microbial removal, clarification of fermentation broths, or in food or beverage applications such as plant extract clarification, gelatin or wine clarification, and so on. Ultrafiltration. Actually, ultrafiltration is not fundamentally different from microfiltration. The separation mechanism in this membrane is based on size exclusion or particle capture. As you can see in this animation, ultrafiltration membranes are capable of separating larger materials such as colloids, particulates, fats, bacteria, proteins, and also viruses, while allowing sugars and other low molecular weight molecules to pass through the membrane. Ultrafiltration membrane fall between that of nanofiltration and microfiltration with a pore size range between 10 to 100 nanometer or about 500 to 500,000 daltons in molecular weight. Ultrafiltration membranes typically operate between 3 to 5 bar, of course in some special cases to 8 bar, and are dependent on transmembrane pressure to drive the separation process. There is a wide range of ultrafiltration membranes in the current market, but studies have shown that the ultrafiltration membrane with a nominal pore size of around 0.02 micrometer is found to be the most effective in eliminating potential elements such as microorganisms, cells, algae, and large molecular weight from the feedwater source that are responsible for the reverse osmosis membrane fouling. Ultrafiltration processes are currently preferred over traditional treatment methods for the following reasons. No chemicals required, constant product quality regardless of feed quality, compact plant size, capable of exceeding regulatory standards of water quality, achieving 90 to 100% pathogen removal. Nevertheless, it has to be noticed that ultrafiltration processes are currently limited by the high cost incurred due to membrane fouling and replacement. Additional pretreatment of feed water is required to prevent excessive damage to the membrane units. Now, the previous example has presented for the ultrafiltration. As you can see in this example, the difference between microfiltration and ultrafiltration is the removal of virus using ultrafiltration, but none cannot remove dissolved substances. Ultrafiltration applications. In this slide, some ultrafiltration applications have presented, and as you can see, in addition to water and wastewater treatment, industries such as dairy, chemical industry, pharmaceutical manufacturing, food and beverage processing employ ultrafiltration in order to recycle flow or add value to later products. In drinking water, ultrafiltration can be used for the removal of particulates and macromolecules from raw water to produce potable water. It has been used to either replace existing secondary treatment levels such as coagulation, flocculation, sedimentation, and also tertiary filtration for removal of dry halomethanes employed in water treatment plants. Some applications in wastewater treatment, such as removal of oil from wastewater, clarification of biologically treated effluent in membrane bioreactors, or removal of chemical oxygen demand from industrial effluents. When treating water with high suspended solids, ultrafiltration is often integrated into the process, utilizing primary treatment processes such as screening, flotation, and filtration, and some secondary treatments as pretreatment states. In many cases, ultrafiltration is used for prefiltration in reverse osmosis plants to protect the reverse osmosis membranes. So, you learned about the microfiltration and ultrafiltration, such as pore size range, required pressure, substances that can be removed, and also some applications so far. Let's have an exercise. Describe the removal efficiency of the constituents using microfiltration and ultrafiltration according to the presented data in the following table. This is a tertiary effluent water quality data. At first, I have to say that the treatment processes in wastewater treatment are divided into four levels: preliminary, primary, secondary, and tertiary. Actually, it has to be noticed that in wastewater treatment plant, membrane filtration has to be used after tertiary treatment level due to the low constituents concentration in this level for prevention of the membrane problems such as fouling and scaling. We will discuss about these problems in the next section. In this table, tertiary effluent water quality and rejection characteristics of microfiltration and ultrafiltration membranes have shown. Description. To describe these constituents, I selected TSS, nitrate, TDS, and microorganisms. TSS, or total suspended solid. If you look at the size range of TSS in this figure, All the suspended matters are between 1 micrometer to several millimeters and can be removed using microfiltration, but colloids located in the size range of 1 to 0.01 micrometer, so that they can be removed using both microfiltration and ultrafiltration, and that's why you can see in the table the removal efficiency using these membranes is more than 95%. Nitrate. Nitrate is an oxidized form of nitrogen. Nitrate usually exists in groundwater as a result of the percolation of the pesticides, fertilizers, and etc. on groundwater. The nitrate ion is a polyatomic anion with a molecular mass of 62.01 Dalton, and if you look at the molecular mass range in this figure, it cannot be removed using microfiltration or ultrafiltration. For this reason, the removal efficiency for both is almost zero. Two of the most important processes for the removal of nitrate are ion exchange and reverse osmosis. TDS. TDS, or total dissolved solids, including cationic and anionic ions such as sodium, chloride, potassium, calcium, and etc. TDS depends on the charge capacity, can be removed using nanofiltration and reverse osmosis, and as you can see in the table, the removal efficiency of TDS for microfiltration and ultrafiltration is almost zero. Microorganisms. Here the main microorganisms in water and wastewater according to the diameter size have presented. Microorganisms such as Protozoa, Giardia lamblyaceae, Cryptosporidium, bacteria and viruses, and all they can be removed using microfiltration except viruses, and as I have already mentioned, viruses can be removed using ultrafiltration, and for this reason you can see a significant difference in removal efficiency of viruses between microfiltration and ultrafiltration. Now, please do the remaining constituents yourself. This is your task. Nanofiltration. Nanofiltration is a membrane filtration-based method that uses nanometer-sized through pores that pass through the membrane. Nanofiltration membranes have pore sizes from 1 to 10 nanometers, smaller than that used in microfiltration and ultrafiltration, but just larger than that in reverse osmosis. As you can see in this dynamic image, nanofiltration in comparison with ultrafiltration can remove sugars, amino acid, multivalent ions such as calcium, magnesium, aluminum, and etc., but not monovalent ions such as chloride or sodium. The permeability of the nanofiltration membrane is higher than that of reverse osmosis, while the extent of removal of germs and heavy metals is similar due to their large molecular sizes. Nanofiltration provides sufficient minerals required for human consumption between 60 to 150 ppm TDS, including sodium, magnesium, potassium, calcium, phosphorus, whereas reverse osmosis removes all of the minerals from water and could be harmful in the long run if the water is not remineralized. The highly compact nature of the nanofiltration design enables its portability to remote villages where higher water recovery between 70 to 80% ensures an adequate supply to the entire village population. A main disadvantage associated with nanotechnology, as with all membrane filter technology, is the cost and maintenance of the membrane used. In fact, nanofiltration membranes are an expensive part of the process. Repairs and replacement of membranes are dependent on total dissolved solids, flow rate, and components of the feed. Still, nanofiltration is the least used method of membrane filtration in the industry, as the membrane pore sizes are limited to only a few nanometers. Now the example has repeated for nanofiltration and you can easily answer it. Specify the substances that can be removed using nanofiltration. Let's look at the answer. As you can see, monovalent ions and low molecular weight organic compounds can pass through the membrane and remaining can be removed using nanofiltration. Nanofiltration applications. Nanofiltration is an innovative process having many applications for drinking water purification and wastewater treatment. The best technology for the removal of hardness from groundwater, because nanofiltration is a most common filtration for softening of water by removing divalent ions such as calcium and magnesium and disorganics such as trihalomethanes and disinfection by products. Some applications in industries such as fine chemistry and pharmaceuticals, oil and petroleum chemistry, bulk chemistry, natural essential oils and similar products, and medicine, and you can see the uses in this table. Reverse osmosis. The finest filtration in membrane family is reverse osmosis. Reverse osmosis is most commonly known for its use in drinking water purification from seawater or brackish water. Removal of monovalent ions such as calcium and sodium that have a molecular weight 150 to 250 Dalton that is not possible using nanofiltration. The maximum required pressure for reverse osmosis is between 10 to 100 bar depending on its application to push the fluid through the membrane, and driving force is also usually provided by pump. The most operation mode of reverse osmosis is the cross-flow mode to allow the membrane to continually clean itself, and it's very important for recovery and increasing the lifetime. In general, the order of rejection of ions by reverse osmosis membranes is as shown here. For cations and anions, as you can see, from ions with more charge to ions with less charge respectively. Now specify the substances that can be removed using reverse osmosis. And as you can see, all the substances can be removed using this membrane, and only water can pass through the reverse osmosis. There are many applications for reverse osmosis. For example, in drinking water, preparation of pure water, drinking water purification, sea and brackish water desalination, or in tertiary treatment of wastewater for water reclamation, in the power industry such as boiler water supply, the electronics industry, in semiconductor industry, ultra pure water, food industry in prescription water, water production, tea, fruit juice, vegetable juice, and plants, the thermosensitive material extraction and enrichment. In beverage industry, formulation of water, production water, wash water, and some applications such as the pharmaceutical industry, chemical industry, petrochemicals, and so on, as you can see here. In this table, a list of constituents and expected rejection values of nanofiltration and reverse osmosis membranes on tertiary effluent has presented. If you look at the monovalent ions such as sodium chloride, calcium chloride, and fluoride, you can observe a significant difference in rejection rate between nanofiltration and reverse osmosis. But for example, in organic compounds such as sodium sulfate, magnesium sulfate, or hardness, and there is not a significant difference between them.